So as we have seen in these sessions, there's a lot of excitement around measuring this global signal. And specifically what I would like to go over in this talk is some of the exciting science that we hope to be able to tease from a measurement of the global signal, rather than some of the systematic challenges to building an array to observing this. And one of those has to do with dark matter, the stuff that all astronomers' dreams are made of. But one of the problems, of course, is that in the early universe, when the first stars are forming in the cosmic dawn, they're giving off light that is often going to, as Steve Ferlanetto said in his talk, there's many unknown unknowns. And so what we do know is that there's going to be this light that is going to create the 21 centimeter signal. And the question that we want to be able to answer is, beneath all of that, can we actually tell something about dark matter and the underlying dark matter distribution that is giving rise to this kind of star formation and the kind of light that we will see that will produce that signal? So the astrophysical signatures of the stars, we want to separate then from the cosmological signatures due to dark matter. We're going to, the reason, of course, that we're so interested then in this is the dark matter problem in general, right? So everywhere we look on the scale of galaxies and larger, dark matter is ubiquitous. We need it to understand the dynamics of elliptical galaxies, the kinematics of spiral galaxies, gravitational lensing, clusters and clusters crashing together, as well as cosmic structure formation from the cosmic dawn. All of these things point to a need to understand, of course, dark matter. And the global signal then allows us to measure dark matter in ways and in epochs that we haven't been able to do before. By specifically, we're going to constrain structure formation. So the one on the bottom right, you can see the picture of the CMB anisotropies is related to how we're going to constrain the global 21 centimeter signal. So in the standard paradigm of cosmology, dark matter is cold. And you can see this figure on the right. Oh, that warm dark matter should be in the middle column. But on the farmost column here, you can see that in the case where dark matter is cold, the particles don't have high streaming velocities. And so they tend to clump together and form a lot of small halos. Whereas if you increase essentially the thermal velocity or decrease the mass of dark matter, they start to spread out and diffuse faster and faster before they can collapse into these dark matter halos, as we call them. And that's what you get with warm dark matter in the middle and then hot dark matter on the right. And you can see, especially in the case of hot dark matter on the right, that the structure formation has completely diffused all of the smallest halos. And the smallest halos we think are going to be very, very important for the first stars forming in the galaxies, which will affect the global signal. And so the number then of these small halos is a key ingredient for measuring how much light is going to be produced by the early universe, and thus the exact shape of the global 21 centimeter signal. So just a brief recap, once again, from everything. You've seen like 1,000 of these plots, but the essential thing to note here is that when the first sources turn on at cosmic dawn, shown by the red arrow there, depending on the number of sources, we're going to get more light, and that's going to deepen the trough before the heating begins from the X-rays from the first black holes left over from these remnants. And also it'll affect the timing of reionization, because essentially more photons means that we're going to reionize all of the gas in the IgM quicker. And so if you have more dark matter halos, more of these small dark matter halos, then you get more sources, which means more photons, which means things like the trough can be deeper, reionization will finish sooner, etc. So the big question then is, given all that we need to know about dark matter and also about the astrophysics of these first sources, can we still say anything about this underlying distribution of dark matter? And so what we have to do first then is to add different models for dark matter into our simulations of the global signal. And so what you see here on the right is just essentially the number of halos as a function of halo mass. And so for cold dark matter, there is no truncation, as you can see. There's just a increasing number of low mass halos all the way to the 10 to the 5 end. Whereas if you have warm dark matter, once again, where the dark matter particle is actually slightly faster, has a higher thermal relic velocity, then you diffuse these small halos, as you can see by the truncation in the dotted and the dashed lines. And so this is how we put it into our signal. We now have a method for incorporating the number of halos. Now that we have the number of halos, we just put a star in each one of those halos, and then we calculate what the global signal should look like. And so you can see, for instance, if you concentrate on the right plot, which is for a particular star formation parameterization, that if you increase the warm dark matter mass, you get closer and closer to cold dark matter. You have more halos, which means that the global signal shifts to earlier cosmic times. There's just more light produced because there's more galaxies. Another thing actually that this signal will allow us to do that I just wanted to only mention briefly is also to put constraints on the first generation of stars, which are hypothesized to exist in the first metal-free halos called POP3. If they do exist, they're going to be enormous, probably on the order of 100 solar masses or so. And those are also going to leave an impact on the signal, as you can see by the cyan and magenta lines there. And so any deviation that we see in this cosmic dawn from what we expect for cold dark matter is going to be an indication of new physics. And so what we did was we ran a Fisher forecast with all of these astrophysics parameters included, as well as the warm dark matter parameter, which is the mass mx, to see if we could still, in the presence of degeneracies between all of these astrophysical parameters, extract something meaningful about dark matter. And the answer is that actually we can, even when you include systematic effects from models, which is shown by the dashed lines, the black dashed lines in each of these. And you can see in each case, if we include POP3, which are the two on the right, or if we just have POP2 signals, for a given input warm dark matter mass, in this case 7 keV, we can still get very excellent constraints on the dark matter mass, which is very, very encouraging. It tells us that essentially the global signal is a perfect test bed for measuring the thermal mass of dark matter and then putting constraints on structure formation. And this is quite unique, really, in this structure formation measurement to the global signal. So in conclusion, dark matter then we think should have a very discernible effect upon the structure formation of the early universe, and thus the amount of light that we'll see from it. And if we measure the global signal, then we will be able to hopefully put constraints on this in epochs nobody's measured before, and fundamentally measure dark matter in its mass, which will tell us something, right, about what kind of particle dark matter could be. That's what I have for you. Thank you.
All right, thank you, Joshua. We probably have time for one quick question, if anybody has one. I don't see one online. Jack, please. Oh.
I was just going to say, Joshua, can you talk a little bit about what is the motivation? You know, for a long time, CDM was the model. So what is motivating us, or the community in general, to start thinking about alternatives like warm dark matter?
Right. Yeah, that's a good point. I should have mentioned that. That in particular, there's been a couple of emerging conflicts between the standard paradigm cold dark matter and what we're observing now. So in cold dark matter, as I said, there's a lot of small halos predicted, but recently measurements of like Milky Way galaxies and satellite counts, this is called the missing satellites problem, have come up with a large discrepancy. Rather than seeing hundreds of these satellite galaxies, we're seeing something like 10. Or with a similar problem is the so-called too big to fail problem, named around 2008, which is that there are halos that are large enough that should be hosting galaxies that don't. And so these are all cases of where there should be galaxies that have diffused out. And one way to very elegantly explain that is to just make dark matter warm rather than cold. And in that way, you still keep all of the constraints on large scale structure formation that still exist, while also removing the discrepancies with small scale structure.